What's going on, math people? We are back again, and this time we're talking about the monotonic functions. Let's just break this down. Monotonic is simply going in a specific direction. So monotonic is constantly increasing. This would be called monotonically increasing whenever it's rising from left to right, or it's constantly decreasing, monotonically decreasing. So the math talk, whenever you're talking about monotonic increase and decrease, this is saying that the y values, so you have, if you're on an axis, let's say we have this happening right here. This is x1, x2, x3, and so on. Here is f of x1, that's the first y value, f of x2, f of x3. If you notice, as the x's progress, the y values are all increasing. They're all greater. So this is saying that f of x1 is less than f of x2, which is less than f of x3. Monotonically increasing. Similar setup for decreasing. So if we're talking about monotonically decreasing, you have x1, x2, and we'll stop at x3, but it can go on and on and on. And here we go. Monotonically, we start off high, and then we start going down low. All right. And so this would say f of x1 is greater than, and it just keeps going like this. All right, so, but let's get this into some calculus viewpoint, right? All right, that's understanding some basic algebra concepts for monotonically increasing and decreasing functions. All right, there's some things that you need to know. All right, and we're going to be talking about the first derivative test. We're going to be talking about, okay, y'all forgive me, I was watching a little bit of a Trump rally, and my voice started to change. All right, so here's some stuff that you need to know. You have f prime of x if f prime of x is greater than 0. So if the first derivative is greater than 0, and this is true for every x value, in an open interval AB, then the function is monotonically increasing, and f is increasing. All right. So shorthand, I would say f prime greater than 0, I'm going to be increasing. That's my little symbolic notation. Likewise, you have the same layout. All of this other information remains the same. X is in the open interval. And just so that you all know that f is a differentiable function, the assumed case is that f is a differentiable function. You also have this guy taking place. So my symbolic layout would be, all right, if my first derivative is negative, then I'm going to be decreasing. My first derivative is positive, I'm going to be increasing. All right. So let's jump into a problem, right? All right. The problem was going to ask us some stuff. It says Find the critical values. Find the critical point values. Finding critical point values. Like, what are critical point values? All right. Critical point values are values that make the first derivative values that make the first derivative 0 or undefined. All right, so jumping back into the example, when it says find the critical point values of a function and identify the intervals of increase or decrease, we'll use those critical point values. So the function that it gives us is f of x equals x. Wow, way to write it twice. F of x equals x cubed minus 12x minus 5. All right, so in order to find out where the function identify increasing and decreasing intervals. All right, so jumping into our example, we have f prime of x. First thing we need to do is find these critical values. F prime of x equals 3x squared minus 12. Took the first derivative. There is nothing that would make the first derivative defined. You do not see a variable in the denominator, but there are things that could potentially make that first derivative equal to 0. So we'll find out what those values are. That leaves us with 3x squared minus 12 equals 0. X squared equals 4 whenever you add 12 to each side and divide by 3. And then undoing the squared power, you have plus or minus 2. So that's the two critical values are plus or minus 2. All right. Now to find the intervals of increase or decrease, to find those intervals, you take your critical values and you put those critical values on an interval table. All right. And you would choose numbers between those critical values and plug it into your first derivative. All right, so picking numbers between negative infinity and negative 2, I'm going to choose negative 10. And I put it into the first derivative. I don't care what the value is. The only thing I'm more focused on is when I plug this in, is it going to be positive or negative? I don't care what the value is. I see that this is going to be positive. Choose a number between negative 2 and 0. Plug it into the first derivative. I can care less about the value. I just want that the sign is negative. And then I do the same thing over here and I have positive. So now I have my intervals of increase or decrease. My positive locations identify intervals of increase. So I'm increasing from negative infinity to negative 2. And again from 2 to positive infinity. So increasing. And I'm decreasing from negative 2 to positive 2. My function is decreasing. All right. Now, let's move on to a bit more challenging example, because there's some other things that you can glean from this. Let me just add on to this example. I want you to follow with me right quick. All right, right now we are increasing, and then we start decreasing. So if you look at this, you can follow that you are on the top of a hill. So that's telling you that you'll have a max right there. And if you go to the next critical value, you see you're down in a valley because you start out decreasing, and then you go into increasing. So you're going to be at a minimum right here. All right. So that's just some insight to give you where you can find more extrema. We talked about extrema in the past with the extreme value theorem. But let's dive into a heavier example. All right. Check this guy out. And let's take this one. Done. All right. It says find the intervals on which the function is increasing and decreasing. So I'm just gonna go ahead and rewrite our example right quick so it can be bigger for us to see. We have f of x equals x squared minus 24 over x minus 5. And then it gives us the domain, x cannot equal 5. All right. Part A wants us to find the intervals of increase and decrease. All right, so in order to find those intervals, we have to first find the critical values. Finding the critical values, we know we need the first derivative. So f prime of x, we'll use the quotient rule. Derivative of, you take the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. All right. And simplifying, after we simplify this, we have 2x squared minus 10x minus x squared plus 24 all over x minus 5 squared. That equals x squared minus 10x plus 24 all over x minus 5 squared. All right, so now we see that we have a potential place to have critical values that make the first derivative 0. When we factor that numerator, this numerator factors to be x minus 6, x plus x minus 4 over x minus 5 squared. So places that make it 0 are when x equals 4 and 6. And the places that would make your first derivative undefined, we're looking at the denominator when x equals positive 5. And the way we did that, we set the numerator equal to 0 to get the zeros location, and then to get the undefined location, set the undefined as 0. Draw yourself an interval table. Coming from negative infinity, there's 4, 5, 6 to infinity. put all your critical values on. And then again, you just run through the same process of plugging in values and seeing how it play out within the first derivative. We go and plug these values into the first derivative, and this will produce something that becomes positive. Between 4 and 5, I'm just going to choose 4.5. That's going to produce something that is negative. Between 5 and 6, I choose 5.5. Also produces something that's negative. And between 6 and infinity, I'll just choose 10 again and produce something that's positive. Each of those values, remember to plug those values inside of the first derivative. All right, and we have positive from negative infinity to 4. We're increasing. We're decreasing from 4 to 5. And we're still decreasing from 5 to 6. And then we're increasing again from 6 to infinity. Okay? And we found the intervals of increase and decrease. It says identify the function's local and absolute extreme values. All right? In addition to using this, identifying the local and absolute extreme values, remember, when you're on the hill, increase to decrease, you have a max. Nothing's happening here because it's constant. Then we have decrease to increase. That gives a minimum. So those are local values. But I also want you to be able to visualize this in a calculator. So we're going to take our function and drop it off in the calculator. X squared minus 24 over x minus 5. X squared minus 24 we have x squared minus 24 divided by x minus 5 and graph it. Okay, so as y'all can see here, that dashed line, that's the vertical asymptote. That's where the function is undefined. All right, what I want you to notice here, right there at 8, you see that there's a local max. And we also see at 12, we have a local minimum. So the value of 4 produces that local max at 8, and the value of 6 produces the local minimum of 12. But we cannot identify the absolute max because this function is increasing forever. And we cannot identify absolute min because it's decreasing forever. All right, so be able to utilize your software. And with that being said,